Last but not least, we have this table problem. It looks like a train. And you know, this late at night, I keep thinking of it as a train problem, but it's just a table. Let's read carefully what it says here about these tables. This is kind of an introduction to sequences and series, and I want to help everybody kind of understand this, because we're going to be moving into those a little bit more when we hit geometry and some things like that, especially in 8th grade. But it says in the diagram below we have a certain number of identical tables. The number of tables is n. Sometimes we have 1, sometimes we have 2, sometimes we have 3, all the way up to however many we want, represented by this variable n. Okay, so we have n tables, and they're joined end to end to form a long table. One table can have 2 seats on each side and 1 seat at each end. So if I just had one set of tables, I'd have a chair and 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 a chair. I would have 6 total seats. Is that okay? It says a single table can have 2 seats on each side and 1 seat on each end. That's 6 tables. And then it says complete the following chart. And it says n, and when we're asking ourselves when n is 1, how many seats are there? Well, we just drew that picture. When n is 1, how many seats are there? 6. Well, when n is 2, how many seats are there? Well, let's forget for a minute about these ones in the middle. If there are 2 right here, how many seats are there? Well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 seats. When n is 3, how many seats are there? Well, let's forget about this one. And since these are bumped up together, we can't have a seat on the end of this or on the end of that. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and those 2 that are on the ends again, 14. And I noticed something very quickly, that the difference here is 4 every single time. In fact, my guess is that this is 18. Let's see. There are 4 tables, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and those 2 that are on the end, 18. Okay, so now I have to imagine that there's another table. Oh, no, I don't. I can just add 4 because I recognize that the pattern is adding 4 every time, right? So that chart's now filled out. But then it asked me this question. If n tables are joined to form a long table, express the total number of seats in terms of n. Well, if there's one table, it's 1n, because n is 1, n plus 2. If there are 2 tables, it's 2 n's, 2 tables, right? That's how many tables there are, so there are 2 tables. And then plus these 2 seats on the end. I think. Well, let me think about that. 1 table, 2 times 1 plus 2 is 6. Oh, I get it. For 1 table, doing a think aloud here, I have 4 seats. For 2 tables, I have 8 seats plus 2. So for 1 table, I have 4 seats plus the 2 ends. For 2 tables, I have 8 seats plus the 2 ends. For 3 tables, I have 12 seats plus the 2 ends. Oh, so for 1 table, I have n, but I multiply it by 4 seats because that's how many, and I always add 2 for the ends. So for 1 table, 4 times 1 plus 2 is 6. For 2 tables, 4 times 2 is 8 plus 2 is 10. For 3 tables, 4 times 3 is 12 plus 2 is 14. For 4 tables, 4 chairs times that 4 tables is 16 chairs plus 2 more is 18. That will describe how many chairs I have no matter how many tables I'm working with. This is an excellent problem because when you're an engineer, once again, or a scientist, and you're working with chemistry and you're working with bonds and you have 15 million different atoms and they're all bonding the same way, you can use chains of atoms and talk about how many free electrons there are in that chain of atoms, and you can use this kind of thing to really talk about that in very concrete terms. Even though this seems very abstract, I can use it to describe something as concrete as tables or atom chains, fatty acid chains, things like that. So study that for a bit. See if you can make a connection between this and the number of chairs at the tables.